Assalamualaikum again and good morning. Can you see the slide now? Can? Okay. Right. So today's topic will be LU3, which is one-way analysis of variance, or simply known as ANOVA, one-way ANOVA. So we have covered LU1 and LU2 before. Okay. So this is what we have studied before. In LU1, it's a very simple LU. We talk about some basics of statistics like average. Yeah? Average and mean is the same. Mode, median, right? And then that is measures of average. And then we also discuss about measures of spread or dispersion, variability. So make sure you know what does the word spread, dispersion, variability means. Yeah? Dispersion is how dispersed the thing is. Dispersed means like how scatter, how in Malay, how apa ni, berselerak. Spread is in terms of how wide your data is. Okay, and those characteristics are measured by parameter called variance and standard deviation. Okay, so variance is like this one, the symbol is called that symbol is called sigma, but variance has s squared, and standard deviation is like this, the symbol. Okay, so this is in LU1. Okay, I suppose you also have studied this in your previous background, like maybe Form 6 and Form 5, or even matriculation. Okay, so this is just a revision for you. And in LU2, we have talked about binomial Poisson. Yeah, this is LU2. If you guys cannot hear me or cannot see the things that I show to you, please stop me at any time, because I might not aware of the chat. I just talk here. I don't have the chat box. I mean, I don't open it. So please shout out. Okay, please stop me at any time if you have any question, or if you have anything is not working on the screen, or you cannot hear my voice. Okay, right. So in LU2, we talk about discrete distribution. Okay, so first you have to know what is discrete and what is continuous. Yeah, discrete means it's just one number, yeah, without decimal points. Like is a whole number. Yeah? So under that discrete distributions, we talk about binomial and Poisson distribution. Okay, binomial, the difference is in terms of the n. Yeah, for n is more than 20, we use Poisson, but if you have less than that, you use binomial. It has, binomial means there are two options, yes or no, male, female. Yeah, true, false, something like it has two outcomes. So that's why it has it is named as bi, two. That is discrete distributions, and after that we talk about continuous distributions. Continuous distributions means, continuous means it has decimal points in terms of the number. So for example, like height, I mentioned before, right? 150.1, 150.2, 50.3. So there are people who have those height. Yeah? So the distribution is continuous. So that's why it's called continuous. So under continuous distribution, we talk about normal distribution. Normal means, when we say normal, it's always the bell-shaped curve. Yeah, this is normal distribution. We also talk about T distribution. Yeah, and in this one, we have various circumstances, like various situations where we know the standard deviation, we do not know the standard deviation. We have one sample, we have two samples, right? So those are the things that we have covered under normal and T distribution. You can see my scribbles as well, right? This the one that I jot down on the slide, guys.
Yes.
Anyone? Yes. Okay. So apart from that, in LU2, we have also talked about how we want to compare one sample. Is it okay? One sample which leads to, I mean, when we talk about sample or in statistics, we are always concerned with mean, yeah, with the average, mean or average. So this one is one sample, and we compare with, like we want to see how that sample can represent the population. Is it okay, guys? I heard someone say something. Is it okay, guys? Okay, I need someone to say okay, just okay.
Director.
Okay, clear? Is it? You can hear my voice clearly, okay? Right?
Clearly.
I know that my office is quite noisy because of the aircon, the blower. Yeah, I hope that it doesn't interfere with my voice. Okay, so we have talked about one sample, how we compare a sample and the population, right? And this will lead us to this sort of hypothesis, whereby we just say that mu, because we are talking about mean, right? So we developed the null hypothesis and the alternative hypothesis based on one sample, okay? And then we move to two samples, whereby we compare two means. Two means means the mean come from one sample, so two means two samples. So we want to see whether the two samples have a difference or not, okay? And that gives us to this extension of hypothesis. So you see the first case where it is only one sample, we just say the mu of only one sample. We don't have to denote it with one or two, because it's just one sample. But when we talk about two samples, we have to label properly mu1 and mu2, right? Because we are comparing those two samples. So the null hypothesis says that there is no difference between the two samples, right? And the alternative hypothesis is the opposite. So in general form, we can say it is not equal. But if we are given a situation, a more specific situation, then we can use the symbol less or greater. Yeah, less or greater. I mean, this one can be written as well as mu1 greater than mu2, or sorry, this one is less than mu1 less than mu2, or you can also say mu1 greater than mu2. Okay, so this one is like the mu is moved to the left side, so that's why it leaves with 0. Yeah, and also for the null hypothesis, you can also say that for the two samples, mu1 is equal to mu2 instead of putting this kind of equation. Okay, because if you move this one to the left, it will left the right side with 0 value. Yeah, either one is correct. Okay. So that is in the case of two means or two samples, and we have discussed about different situations where in the case of two independent samples, we use normal distribution, and if they are dependent, right, and we do not know the standard deviation, then we use t distribution. Okay, it depends on the situation. Okay, so now that is two samples, one sample and two samples. So what happens if we want to compare more than two samples? Okay, so the reason why this topic is related to science, or you are in zoology, right? So it will be useful for you to apply later on when you carry out your research in your third year or in your FYP. It's because you want to analyze the data. It's not just about collecting the information whatsoever from your, I mean, regarding the zoology things, field, but you have to analyze the data, whether the data makes sense or not, whether there is a difference or not between one sample to another. Okay, so that's why we teach you in the first year. Okay, let's say in what situations, what kind of, for example, experiment, let's say you are comparing between species, species A and B, right? Okay, and species A, you have certain values, right? Certain data. And species B, you also have certain values or data. So this is within the sample for each of these, within the samples. So this is like an example, I mean, let's say you want to compare what? You want to compare perhaps the morphology of the animals or the insects, the animals there. You are in zoology, right? I'm not really expert in giving an example in zoology. Okay, that is in the case of two samples, but in reality, we would have more than two samples in any experiment. Yeah? We would have more than two things to be compared. So that's why you need to know this test called ANOVA. Yeah? So in the case of, let's say you want to compare more than two species, like 3, 4, and 5, and 3 at least. More than 2 means 3, 3 and above. Huh? It's not only 3. It can be 3, 4, 5, and so on. Okay, so you need to use what we call ANOVA, analysis of variance test. Okay, so this is what we are going to cover in this topic. So some introduction. ANOVA, it stands for analysis of variance. Okay, analysis of variance. In this chapter, we are going to cover on the one-way ANOVA. We call it one-way. So ANOVA is divided into one-way and also two-way. But we cover first one-way. Yeah? So what is meant by one-way? But before that, as I mentioned just now, ANOVA is used when there are more than two groups. Groups, samples, treatments are the same. Samples, sometimes the terms are used interchangeably. Sometimes we use samples, sometimes we use groups, sometimes we use treatment, but it's the same thing, okay? Samples or treatments. So you might see those words are being used like in some situation, but it refers to the same thing. It is actually groups. So ANOVA is used when there are more than two groups to be compared, okay? And if we have just two, we can use t-test. Student t-test, we call it. Yeah? But if you have more than two, we use ANOVA. Okay, and why is what is one way and two way? So we are going to cover only one way. So one way here refers to factor. Okay, factor. So way here is referring to factor. So what is factor? So for example, if you want to compare, now it's ANOVA, you have like more than two samples. So species. Species A, B, and C. So there are three samples, right? Okay. Species A, or maybe a species sample, sample. Okay. So sample A you got from maybe Cebu. Okay. You are in zoology. You are going to do lots of field trips, because you are going to collect certain samples, animal samples. So it refers to certain areas. Yeah? So let's say this one is maybe Kuching, yeah, Kuching, and this one is Miri. Okay, this represents your samples. Okay, and you are going to apa ni? Maybe this one is referring to certain species, and you want to analyze perhaps try to give an example in zoology. Apa ya? The diameter of apa ya? Maybe the size of animal lah. A very bad example. Size of apa ya? Size of insect lah. Insect X lah. I do not know the name of specific insect. Okay, size of insect X, and you want to compare the data that you got from Cebu, from Kuching, and from Miri. So each of these represents sample, right? Okay, so what is factor now? So let's say factor is the size here, the size. Okay, size. Okay, maybe another one is weight. Let's say I just want to give you example of things to be compared. So let's say you just want to compare size. Size maybe the diameter of the insect, or maybe the length of the insect. Okay, so that is referring to factor. Okay, one factor. So you want to compare across the samples, like the samples you got from Cebu, samples you got from Kuching, samples you got from Miri, how the size of the insects vary. Is it Kuching is more, or the samples of Cebu is more, and stuff like that. Okay, so in this case, the factor is referring to the things that you want to measure, or the parameter. Sometimes we call parameter, sometimes we call variable. Okay, so it's only one. Let's say you only want you want to consider this. But if let's say you want to increase more factors, let's say you want to add another one, weight. This is factor one. Yeah. Apart from the size, you want to also measure the weight of the insect that you have sampled in each of the places. So this is another thing that you want to measure. So this is factor two. Okay. So if you have only one factor, you want to compare only size. So it means that your test, the test that you're going to carry out is one-way ANOVA. Okay. But if you want to compare the size of the insect and also the weight of the insect across the samples that you have, this is, I just give 3 examples, but it can be more. That means the ANOVA test is called two-way ANOVA. Okay. So way here means the factor or variable. Yeah? And the variable is independent. The reason why it is independent, it doesn't actually have any association with the weight. Of course, we know that if let's say the size is big, of course the weight could be big. But then what I mean here is that you can always carry out the analysis of the size without the weight, or you can carry out the analysis of the weight without the size. You don't have to, it's independent by nature, okay, the factor. So that is what is meant by a way, what way indicates. Yeah? Right. Normally, we analyze up to 5 levels, but theoretically it is unlimited. Okay, what is 5 levels here? Level means that you want to set certain level, or maybe macam size tadi. You want to divide it into how, macam contohnya apa ya? Upper level. Contohnya lah, I don't know lah the exact term for ni. Excuse me for that, or maybe lower level. Okay, lower level of the insect tu, macam contohnya you have contohnya certain things kan, upper level lah and lower, something like that lah. But don't refer to my term. You have to go specific to your field, to your apa ni, niche term. I just give you an example, easy example. Okay, so means that mungkin you check dulu dekat upper level of the insect, what is the diameter, what is the size, and then the lower level is what. Okay, so here means that you divide the factor into levels. Okay, this is levels. So in statistics, we also have this term that you have to take note, and we're going to use very frequently. Yeah, levels is the division of the factor that you want to analyze specifically across the samples. Okay, for example, just now you divide it into upper and lower, and you want to analyze throughout the samples that you have from Cebu, from Kuching, from Miri. So how is the upper size of the insect, the size of the insect vary from sample A, from sample B, from sample C. So this one is called level. This level 1. Okay, obviously if let's say you have upper and lower, so it's the first level upper is upper, and the second level is lower. So you have 2 levels. But actually you can have more than that. It's not just 2. I just give these 2 examples. But it will actually contribute to the complexity of your measurement. The good thing is that it will be more specific. You know how those specific area varies from one sample to another, but the challenge to the operator or to the researcher is that it will be more complex because you have more data, yeah, and you have to do more measurements. So it will contribute to the complexity of the data measurement or data analysis. Okay, so that is levels, right? So any questions so far? Do you understand what I explained here?
Yes.
Yes. Okay, it's clear. Okay, thanks. So I give you another example. This is just now about zoology. Kan? Let's say I give you example of a very easy research. Maybe you want to check what you guys like. You guys suka online shopping ke? Okay, I want to see like how this is FSTS is our faculty. FK is Faculty of Engineering, Kejuruteraan, and then this one is FEB, Economy. Okay, so I want to see uh, the the factor is, I give this is another example just to give you, maybe I give you another example, another sample lah, so that dia banyak sikit. Bukan ni 3 saja, is more than that, ANOVA. Another faculty is apa? FAK, Applied Art or something like that. Yeah, I think so. Okay, so you want to check, this represents samples, okay? And obviously you want to compare the samples because there are more than 2 samples, so you have to use ANOVA. And the factor that you want to analyze is the trend of online shopping. The trend of online shopping, maybe amount of things that you spend on online shopping. Okay, that is a factor. Okay, how much? Maybe amount. Okay, so so that is a factor. This is the samples. And how about the levels? Let's say you want to check on year 1, year 2, and year 3. I hope you can see my scribbles here. Okay, this is level. Year 1 student. Sorry for these scribbles. Okay, let's say Y1, Y2, Y3. Okay, these are the levels. Let's say I just set 3 here. So means that the levels, there are 3 levels. And you want to compare across the samples for Y1, okay, how the students from Applied Art faculty spend on online shopping, how the year 1 student of FSTS spend on online shopping, FK and FEB. So that is across one level. You can see different samples. Okay, year 2, macam mana pula? Year 2 and year 3, okay, the same thing. But you can see that for every sample, of course, it has all the year 1, year 2, and year 3 students, right? So let's say this one, the N is 50. N is the number of students. So in this faculty, 50 of students comprises of year 1, year 2, and year 3 students. So that is within the samples, okay? So that's how you see how you analyze or overview the data, the data distribution, okay, within the samples and across the samples, okay. So that is actually the importance of levels. If you don't have levels, let's say you just generalize all the students regardless of their year. So you want to compare students of FACA faculty and then FSCS, FK, and FEB, regardless of the year. So that is throughout without levels. Okay. So the good thing about levels is that it gives you specification, but the downside of it, or the challenge, is the complexity. Like, you have to do lots of things. You have to measure specifically. You have to analyze specifically. Okay. Right. So that is the second example. I think that's quite. I hope that is clear to give you an idea what is ANOVA, what is samples, what is factor, and what are levels. Okay. Right. So we move to the next slide. Okay. So similar to normal distribution, similar to T distribution, we are always trying to compare the means. Yeah? So for each sample, we always concern with the mean. Yeah? Let's say we have 3 samples today. We have to find out what's the mean of sample 1, what's the mean of sample 2, what's the mean of sample 3, and what's the mean of sample 4. So mean is the average, because that represents the whole data. You cannot present the whole data because each of the sample might have big size, maybe n equal to 50 macam tu kan. So it's not wise for you to present all the data. So that's why you have to find what is the mean that represent the whole sample. Okay, so that applies to other tests in statistics as well. So in ANOVA, we want to compare how mean of sample 1 differ with mean of sample 2 and 3 and so on. It depends on the problems that you analyze. If you are given 3 samples, so you analyze 3. So if you are given 5 samples, you have to analyze all of the 5 samples. Okay, so this one is actually depends on the problems that you analyze. Okay, but the minimum is 3. Depends on the problem. Okay. So the null hypothesis always say that there is no difference, nothing happened. Okay, nothing happened means that mu1 is equal to mu2 equal to mu3 and so on. Yeah? So there is no difference, or in other words, there is no difference. That is always null hypothesis in any test, yeah? Not just for ANOVA. For the alternative hypothesis, is always the opposite. Okay, meaning to say that if the null hypothesis says that there is no difference, the alternative must say that there is a difference. But how you're going to say the difference? Before this, for the t-test, we only have 2 samples, right? So we don't have problem. Let's say mu1 and mu2. And for the alternative hypothesis, we can always say that it's not equal. Okay, or we can make it more specific, whether greater or less. Yeah, the symbol, it depends on the problem. But when you have more than 2 samples, let's say 3 is the minimum number. So you have 3 samples, mu1, mu2, and mu3. And you want to say that it is opposite to the null hypothesis. We need to say that at least one of the sample is not equal. But how you want to say, what is actually that? What does it mean actually? So let's say mu1 is equal to mu2, okay, let's say the situation happened, and mu1 is equal to mu3, okay, but it happened that mu2 is not equal to mu3. Okay, now you see this is 3 samples, and the possible pair, it could be mu1 and mu2, right? You want to compare like pair by pair, mu1 and mu2. Another possible pair is mu1 and mu3, right? And another possible pair is mu2 and mu3. So those are the possible pairs from all of these 3 samples. So if let's say what you found out in your analysis, this one is equal, this one is equal, but suddenly you found out that mu2 and mu3 is not equal. Okay, so this is enough to make the whole situation or analysis fall into alternative hypothesis. Okay, do you understand? Yes, yes. Okay, so it means that although mu1 and mu2 sama, mu1, mu3 sama, but there is one yang tak sama, is enough to make it fall under the category of alternative hypothesis. Okay, it can be also like macam this one. Let's say this one is maybe 2 of them is not equal and 1 is equal, but still you have to accept the alternative hypothesis in this case. Okay, and this is in terms of 3 samples, which is the simplest situation. If you have more than 3, if you have more 4, 5, 6, and 7, you have to match. You have to create all the possible combination or pairs. Okay, but this is just to explain to you. At least one of the mu is not equal. That's enough to make the whole situation falls under the alternative hypothesis. Okay, right. Although ANOVA is an extension of the two-group comparison, understanding ANOVA requires some shift in logic. Okay, so in t-tests before, we only have 2 samples. This is what I think I have explained here. When we have more than 2 samples, at least 3, or more than that, let's say 4 and 5. Okay, so you have to. This is what I've mentioned before. We have to create possible pairs. Okay, because we want to compare now whether mean 1, mean 2 equal or not, mean 1, mean 3 equal or not. But before that, we have to come up with all the possible pair comparison. Okay, it depends on the number of the samples. So in this case, there are 5 samples. So the possible pairs, you just match one by one actually, like 1 and 2, 1 and 3, 1 and 4, 1 and 5, okay? Sorry. So it's actually one by one, okay? So it's like you can think logically lah, you have to compare one by one. So 1 and 2, 1 and 3, 1 and 4, 1 and 5. And then after 1 is finished, you go 1 first, and then you go to 2 and 3, 2 and 4, 2 and 5. Okay, you don't have to go 2 and 1 lah, because it's actually the same. Yeah, this one is actually the same as 2 and 1. Okay, you don't have to repeat the same thing because it's just a matter of the position, but it's the same thing. 2 and 3, 2 and 4, 2 and 5, okay, and then you move to 3, 3 and 4, 3 and 5, and the last one is 4 and 5. So those are the possible pairs that can be created from these 5 samples. Okay, the more the number of the samples, the more pairs that you have to compare. Okay, the more complex it will be. So another thing is ANOVA uses some simple logic of comparing variances. So what we're going to do in ANOVA is we have to compare a parameter called f. Okay? So I'll show it later, but just go through first the points. So like in any other statistical test before, you have something to measure, right? And in ANOVA, we calculate f. Yeah? And we calculate f, and we also have I give to you the F table. We also have to find the F from the table, and we compare the F calculated and F table and make decision and make conclusion at the end. So the trend is actually the same, but it's just that the things that you want to measure is different from one test to another. Okay, but the idea is the same. You set the hypothesis, identify the level of significance, 0.05 or 0.01, and then you calculate whatsoever the parameter, the statistical test, make decision, and then make a conclusion. The trend is actually the same with other tests. So in ANOVA, okay, I mentioned just now we have to calculate F. So how are we going to find out the F? Okay, I think I skipped this slide. I just go directly to this table. Okay, this is a table that you have to come up with in your workout, in your ANOVA test. Okay. So what is this table is all about? Okay, so just go through first what are the points here. Okay, you must come up with all this table specifically. So this is the values that you have to find out from the problems that is given to you. Okay, but the basic thing is the structure of the table is you must have sorts of variation between or among groups. This is actually samples. Yeah, samples and groups is the same. Okay, variation within the groups. So just now I mentioned that kalau you ada 3 samples, right? A, B, and C. So variation between the samples or groups is between these. But if you are talking about within the groups, so just within this, okay, because each of the sample, it has a sample size of a certain sample size, and A and B and C. Okay, so you want to see also how is the variation within the sample, within, like, let's say 50 students. Let's say the n is 50. So how is the variation within that 50 points of data? Okay, within one sample. So that is meant by within the groups here. Variation is differences of how it varies. And this one is degree of freedom. So you have to find the degree of freedom for the treatment. So from here we term the sample as treatment. But it's the same thing actually. So you just stick to the term treatment for sample, which means the same. Okay. You have to find out what's the degree of freedom for the treatment, what's the degree of freedom for the error. We call within the groups is now error. Okay. And then there is another term, sum of squares. you have to calculate for the treatment. For this one is called SST. Okay, SS is a sum of squares, T is treatment. So this one is SSE, sum of squares of error. And this one is total sum of squares, denoted as TSS. So you have to remember this abbreviation because it's going to be used very frequently after this. This is SST, this is SSE, this is TSS. I'll tell you after this how to find it. This is just a value, an example of values given, but this is not the one that you're going to remember, the numbers, just the parameter. Okay, and then after sum of squares, we have mean square. Mean square, and you also have two values over here. This one is denoted as MST, mean square for the treatment, and this is MSE. Okay, mean square of the error. And finally, you have P. You just ignore P first, because this one, it will be generated if you use statistical software to calculate. But if you just calculate by hand, you just end up with the value of F. Okay, so this is the F that you are going to calculate. But in order to calculate F, you have to calculate first all the parameters over here. SST, SSE, MST, MSE, okay? Because F here, F is equal to MST divided by MSE. Okay, that is the formula. So that's why you have to fill up first all the values over here in order to reach F at the end. Yeah? And it's very important that you be careful with your calculation, because any error in all of these values, it will give you invalid or incorrect F. Okay, so basically this is the what we call Anova table that you have to generate, yeah, or you have to come up with every time you solve Anova problem by calculation. Anova, it can also be solved in this lecture, or in this course. We teach you how to solve Anova by hand calculation, by manual calculation. But actually, in reality, if you do research, you're not going to calculate manually anymore. You're going to use Excel straight away. But this is just to give you some ideas, some basic understanding about what is ANOVA, so that you know that you are analyzing groups, you're analyzing across the samples, you are analyzing within the samples. So that is actually what you have to know fundamentally, okay? All right, so remember about this thing, okay? So how we're going to solve for each of the things just now, and all these SST, SSE, MST, MSE, and so on, okay? So this is the formula. Let's go first for the DF. DF is the easiest one, okay? So DF, so this one is treatment. This is error. This is the DF for the total, or we just say DF. DF, yeah. This one is, you have to say DF for the treatment, DF for the error. Okay, so for the total here, the formula is n minus 1. So if let's say you have the total number of all the samples is, let's say, 50, okay, you just 50 minus 1, so it's 49, okay. For the treatment, it has its own formula. Don't get confused, it's not n minus 1, it's t minus 1 for the treatment. So what is t? The number of treatment, or the number of groups, or the number of samples. Okay, so in this case, let's say is given, this is still an example. So in this case, the example is the number of sample is 5. So the degree of freedom for the treatment in this case is 5 minus 1 is 4. Okay, if you are given 3 samples, means 3 minus 1, so the F for the treatment is 2. Okay, it depends on the number of the samples given to you and the data lah. Okay, this is just example, bukan, it's not the values that you have to remember, okay? So the DF for the error, okay, for the error or within the groups, so we have the formula of n minus t. So you have to identify first n, which is 50, not 49. 49 just now is a df for the n, okay? So this one is in this case like 50, okay? The t is given 5, so it's 45 in this case. So that's why we got 45 here. So the formula is n minus t for the error, for the treatment t minus 1, for the total here n minus 1. Okay. So this is for this column. Okay. Now let's move to the sum of squares, or we call it SS. And when it comes to here is SST, SSE, and this one is TSS. Okay, TSS. This is SSE, and this is SST. So how are we going to solve for the sum of squares? So this is the formula. Okay, I'll give you first the formula and I'll show later how to use this formula. It looks like a bit complex over here. Okay, now SST. So what you have to calculate, although you are given this SSE formula, but you can actually subtract SST from TSS in order to get SSE. Okay, let's go SST first. So this is the formula of SST, the summation of n. Okay, now I think I will update on this I'm not sure whether the one that I uploaded on eLib has this notes. The n here refers to the n of each treatment or the sample size. Yeah, it's not the total n. Yeah? So you have to take note on this. And multiply with the, if you see the thing here is y bar minus y double bar. Okay, so there is a difference of y bar, single bar, and double bar. This is called bar. This thing is bar. I call it bar. In bracket square. Okay, so this one is given to you. It's not actually the formula. It's just an example, the value. But the formula is this one. Okay. So that is SST. Okay, now let's move to TSS first. TSS is given by this formula. So you can see there are double summation. Okay, so this is the thing that you have to be careful. I'll show to you after this how to do this. Yeah, but please take note that there are two summation. This summation, and in bracket yij minus y double bar square. Okay, so y double bar is the overall mean. Overall mean. And the reason why I said just now you don't have to actually apply this formula, because once you know what is TSS, once you know what is SST, SSE based on this formula, right? Because TSS is the summation of SSE and SST. So SSE is equal to TSS minus SST. Okay, so that's why you don't have to calculate by using the formula. Once you know SST, once you know TSS, you can get SSE. Okay. And having said that, if you see, it's very interrelated. The TSS will influence the value of SSE. SST will influence the value SSE. So having said that, you cannot make mistake if you want to get the right answer at the end. You have to be careful with your calculation, and the calculation is a bit tedious, so please be organized in your workout. Okay, that's why you have to be organized, because this ANOVA, it has lots of calculation, and you have to be clear with what you are looking for. Okay, I'll show later after this how to find for this, but let's see first how. Okay, you solve for this one, right? The sum of squares. So once you get the values, like from your calculation, so you insert into this table. Okay, this is, let's say, the value of this, and the value of this, and the value of this, and then just now you have solved for df as well. So MST, how to solve for the MST? Okay, now let's say this one, we have solved this. Okay, how to solve for mean square over here? MST is given by SST divided by df of the treatment. Okay, so this df, this 4 value. Okay, let's say 351.52 divided by 4, you got 87.88. That's how you solve for MST. For MSE is SSE divided by the df of the error, which is 45. So In this case, 453.3 divided by 45, you got this value. Okay, and finally, the F is obtained by dividing MST with MSE. Yeah, so MST divided by MSE, you got this value. In this is an example, 8.724. Okay, that's how you got it. And this is what we call F calculated for ANOVA. Okay, so you can see how very interrelated all those parameters. Okay, the sum of square, the MS depends on the SST, F depends on the mean square. Okay, so be careful with your calculation. So this is F calculated. So what we have to do is we also have to find the F from the table. Yeah? So keep first the value of the F calculated, and you refer to the table. We have this F distribution tables. So how are you going to use this table? I think I have forwarded in the Telegram channel. You can perhaps look in your mobile or maybe later. So what this table is all about is given to you the degree of freedom. Okay, there are two. Let's refer to this. Okay, the degree of freedom. This symbol is sorry. This symbol of, they call it, I don't know what's the name of this symbol. It has the name, you know, like it's not theta. Theta is this one. Okay, degree of freedom. I don't know what's the name of this. So this symbol refers to the degree of freedom. Okay, if you see those value here, this symbol. Okay, and you have to have two values of the degree of freedom. So what are those values? Those values are the degree of freedom of the treatment and the error. The degree of freedom of the error and the degree of freedom of the treatment. Okay, so let's say in this example just now, you got the value of 4 and 45. Okay, remember that value, 4 and 45. So this one is 4 and the degree of freedom for the error is 45. Okay, so how are you going to find the value of F from the table? Okay, by knowing these two values. Okay, so if you have a look at this is the first column is the theta, the DF, and the second one is the degree of freedom. So you have to find out 4 is the one that is on the horizontal part. Okay, this is, I said horizontal. This is for the treatment. Okay, the degree of freedom of the treatment. And this is the degree of freedom of the error. Okay, remember that? And if you have a look at here, there are two values actually given. 5% Roman type, or the one without bold, yeah, the numbers with the non-bold figure, and the bold face or the bold numbers referring to 1%. So what does this mean? This is the significance, level of significance, the alpha, which you have to define, or it is given in the question. Okay, is given, is the normal values is 0.05 or 0.01. So if let's say it's given in the question, you just refer to it. If it's not given, you have to define somewhere in your workout so that I know that the values are based on that particular value of alpha. Okay, so if you see, if let's say we go directly to 4 and 45 just now, so the table is quite long actually, so I just got this one. This is just the extracted form of it. So let's say 4 and 45. Okay, 4 here, 4. But in this table, the value given is 42, 44, 46. There's no 45. We want to find 45. So it's actually, if you think logically, it's somewhere between here, actually 45, right? Okay, let's say find first 4. 4 is here. Okay, so let's say we want to let's say for the value of alpha 0.05, the value will be 2.58, right? Okay, 2.58. If you see this one, 46 ni, 44, that's for 44. 45 is in between. 46 is 2.57. Logically, you can say that it will be 2.575, isn't it? Because it's in the middle. And if you round up these values, it's actually 2.58. So you can just take the value of 44 lah here, yeah, in order to get this value, okay? So it's either one actually. You will actually have to round up to the. It depends. Round up to the nearest point. Yeah. So in this case, that's why I don't take 2.57 because it's supposed to be 2.575, which can be round up to 2.58. Okay. That is for when alpha is equal to 0.05. If let's say the question asks you then with the alpha value 0.01, so the value that you have to find out or to take is 3.78. Okay, the same thing lah. Actually 45 is somewhere here. 3.77 sepatutnya, tapi it doesn't matter. I mean, this is just a matter of 0.01, so you can just put like 3.78 lah also can. Okay, or if you put 3.77, but I terima juga. Okay, it's actually between that actually. Okay, so that's how you solve for the F table. This is F table. So what we're going to do is the same thing like any other test before. You have to compare the F calculated and the F table. So this is the decision rule that you have to remember, right? So if the F calculated is less than the F table, you conclude H naught or the null hypothesis. If it is greater, you have to conclude the H1. Okay. So you just have to actually remember one condition. And of course, automatically you will know that the opposite will be the opposite. So because I always told this to my students before, because normally in the physical exam, face-to-face exam, we don't give this condition to the students. We just provide them with a formula. So that's why you have to remember by yourself. And I would recommend them to remember only one condition, yeah? In order to avoid the mix-up. Otherwise, you would mix up this one with, conclude H naught when it's the other way around. Okay. So that is how you got the F table. So you have to compare the F, right? The F values, and you have to make a conclusion at the end, whereby you have to write down based on the case that you are analyzing. You have to be specific. So in conclusion, you can say that at alpha equal to 0.05, perhaps you want to say you accept the null hypothesis. There is no difference between the means of all the samples, for example. Okay, that's how you write the conclusion at the end. Okay, guys, any questions so far? I'll go how to solve for the SST and so on, but this is just to give you a very general overview about ANOVA. Any questions so far, guys?
Question, Doctor.
Okay, right, thanks. Okay, so what are the things that you need to know as well? Assumptions of one-way ANOVA. The population from which the samples were obtained must be normally or approximately normally distributed. This is the normal assumption that we always make in statistics. Yeah, the samples must be independent. Okay, so it means that each of the samples is independent. It can stand by its own, in other words. Each observation is a random sample and independent of each other. The variances of the population must be equal. So these are for you to know that assumptions in one-way ANOVA. Okay, so this is in general the ANOVA table. What you have to find out, right? The formula of each of these. Okay. And this is the formula of SST and TSS. Okay. Just go through again the steps. Okay, first step, you have to set the hypothesis. Depending on how many samples you have to state it specifically. If you have 3 samples, you put it all the 3 mean, right? If you have 5, then you put 5. And then you have to calculate the degree of freedom for the treatment and error based on the formula that I mentioned just now. Find the mean of each group. Okay, I'll show this one in specific in the problem, but just to give you an idea what you have to find out. Overall mean the mean of all, yeah, the mean of the data for all the samples. Mean of each group or treatment or sample only referring to the each of the sample. Okay, and then we have to find this. Okay, I'll explain this after this. TSS. Okay, basically you have to find what is TSS, what is SST, and from there you will know what is SSE, and then from there you at the same time you have to create that table, Anova table just now that I mentioned, and you have to fill up those values. You calculate MST, MSE, and F. Okay, so this is F calculated. Okay, then you have to find F table. In this topic, we say is F critical, the F table. This is F table, or you can say F table, I can still accept it. And you have to compare these 2 values and make a decision and finally make a conclusion. Okay, so that's basically what are the things that you have to perform in this ANOVA. It's actually quite lengthy, it's quite tedious, I know. So let's have a look at this problem. Let me see where you have it. Okay, that's problem. So this is an example of a problem that requires ANOVA. Okay, and how you want to know that? You can see that there are more than 2 samples. Each of these is samples. There are 5 samples given. Okay, and normally in the question, it's not stated directly that there are 5 samples, there are 3 samples. You have to know by yourself. You have to see the sample. You have to see the data, and you have to know that okay, this is a sample, and there are more than 3. If that is on your own, okay. So you have to take note on that, and you have to learn analyzing the data before you analyze it. This is what we call preliminary sort of evaluation of the data. Okay. So let's say, suppose you are given this question, table below is nitrogen level of this species using Xylon zwageri seedlings after applying 5 different types of fertilizers. Okay. Do the above data present sufficient evidence to indicate a difference in the mean N level for the 5 different fertilizer at alpha equal to 0.01? Okay. Another thing is, if you are given any problem, any question, you have to understand the nature of the problem, what you are going to look at. Okay, so for example, here you are given basically what you want to actually do here is you want to compare how the nitrogen level of this species differ when they are given when this plant or this seedling is given 5 different fertilizers. And in other words, you want to compare the performance of every fertilizer. Okay, this kind of ability to understand the problem is very important, because later on, if you are doing your research, you have to know what you're going to compare and what is your focus actually. And that will lead you to the right measurement of data, the right analysis of data. Okay. So in this case, that is the thing. Before you go to ANOVA, you have to analyze, you have to understand first what you are looking at from this question. You are analyzing the N level of these seedlings when it is given 5 different types of fertilizers. So obviously, each of these is sample, kan? And what these values are actually, these values. This could be perhaps the replication. Yeah? So maybe you measure more than once, and these are the data. Yeah? And at the end, you want to know what's the mean of A, what's the mean of B, what's the mean of C, what's the mean of D, and what's the mean of E. And here also we have another sample, because we want to know how those fertilizers are compared with the control. So this is a bit tricky. It is stated in the question that 5 different fertilizers, but actually the number of samples is not 5, it's 6. Because this is the thing that you want to compare as well with the rest. So you have to add another one here, control. You understand what I'm saying here? And this is a bit tricky, this question. Although it says that 5 different fertilizer, but you are comparing the fertilizer with the control. So the number of samples is actually 6. Okay, that's why I said you have to understand the problem, the nature of the problem, in order for you to understand what you are looking at, what you are measuring. Okay, the number of samples in this case is 6, not 5. Because control in any experiment, you must have control. That one is another information or another knowledge that you should know. So you have to always compare your whatsoever the parameter that you vary with the control. Is there any difference if you apply fertilizer A with the normal fertilizer, or with only just without fertilizer? A control is sometimes is normally the one without any treatment, without any addition of things that you manipulate in the experiment. Okay. Okay, so basically you want to see how it varies. Yeah. Okay. So what you're going to do based on the ANOVA test, we have to set the hypothesis, right? In words, we can say here there is no differences in the mean and level. So you have to know what's the things that you are measuring at the end level in this species or this seedling, using, or this is not really specific. I can say you can perhaps improve this hypothesis saying that there is no differences in the mean of N level in berlian between all the samples. Maybe you can say, or if you want to say, or if you can put it in mathematical form, mu one. What's that? A, is it mu A? Mu A is not A is equal to mu B is equal to mu C is equal to mu D is equal to mu E is not, don't forget, is equal to mu control. Okay, so meaning that there is no difference. There is no difference. It's equal. Okay, I prefer this form actually rather than this sort of any which is fine, but is much clearer when you say like this. Okay. So the alternative hypothesis is opposite. They are differences. Yeah. So you can say in general, because we do not know which one differ, which one is not differ. We just say not equal in general. They are differences. You can also express it like this: mu A is not equal to mu B. Is not equal to mu C. You can see that it's much longer than the t-test because we only have 2 samples in t-test, right? So here you have to mention all the samples specifically. Mu E is not equal to mu control. Okay, so that will be the alternative hypothesis. So the second step, it is given to you actually the alpha value. So you don't have to worry about it, but you just have to take note. Yeah? You're going to refer 0.01, alpha 1 is 0.01. So you have to come up with this ANOVA table. You have to fill up the values of all this stuff. Okay, the degree of freedom for the treatment, the degree of freedom for the error, the total DF, and then this one, the sum of squares. This one is not given. Normally, you have to find out by yourself. I don't know why this. You have to find this one, you have to find this one, and you have to find this one. Okay, so how are you going to find that one? Okay, let's solve for the easiest one, DF. Okay, DF, using the formula, the DF for the total one is, okay, we have a look at the data again. How many samples are here? 1, 2, 3, 4, 5. 5 times 6 is 30, the number of samples. So the N is 30. Okay, so 1, 2, 3, 4, 5. 5, there are 6. 5 times 6 is 30. Okay, now let's find what's the N of the treatment, the N of the sample. Can I have some answer from you guys? What's the end of the, okay, how many treatments are there? First, how many treatments are there? Any answer? How many treatments are there? How many samples are there?
5.
Huh? 5? Not 5.
Sorry, 6.
Okay. So it's T. T is 6. Okay. And what is the size of each of the treatment? What is the size of the treatment of or the sample size?
5.
5. Okay.
5.
Okay. Thank you. So you have to identify that one. So the number of the samples of the treatment is 6. The total data is 30. Okay, so you're going to use that information to solve this one. So here, the DF, since n is 30, so the DF for the total is 30 minus 1 is 29. Okay, that's how we get 29. And for the DF for the treatment is T minus 1. T is the number of samples or number of treatment. So since we have 6 samples, so 6 minus 1 is 5. So that's how we got 5. And the DF for the error is n minus T, which is 30 minus 5. Sorry, T is 6, sorry. T is 6, sorry. So that's 24, okay? So that's how we got 24. So this is the easiest one, okay? Don't make mistake. Okay, next one. We have to solve for the sum of squares. This is a bit lengthy. Sorry, this one, SSE. Okay, this is not given, you have to find out by yourself. So how are you going to solve for SST? This is the data, the original data given to you. I just copied it, okay? But what you have to come up with, you have to extend. This is the workout that you have to do. This is original data, okay? Original data from the question. So this is sample 1, sample 2 until control. Okay, let's go for something easier first. So for each of these sample, you have to find what is the average of sample fertilizer A just now. So you denote it as Y. Maybe here we can put, this one is 1, 2, 3, but you can put YA to be more specific to this problem. E, and control. Okay. So you have to find what's the average. Average is just sum everything and divide by the size. 19.4 plus 32.6 plus 27 plus 32.1 plus 33 divided by 1, 2, 3, 4, 5. You got 28.82. Okay, and you solve the same for B, C, D, E, and control. You got these values. Okay, that's the easiest one. The overall mean, it can be either you just add up all this stuff divided by 5, because it's actually the same thing. You can sum everything, 19.4 plus 17.7 plus 17 sampai 20.8 divided by 30, it will give you this value. But if you use this one, because this one is already the average that you calculated from every sample, you can also just sum of 28, this one is equal to the easiest one, 28.82 plus 23.98 plus 14.64 until 18.7 and divided by 6. You got 19.887. Okay. So this one is denoted as Y double bar, overall mean. Okay, this is the thing that you have to take note. Okay. Right. So the next thing is the next thing, you have to find out what is, okay, let's solve for the SST, okay, because this one you already know what is the y bar and y overall mean. Okay, this one is the formula of SST. SST is equal to the summation of n. N here is referring to the size of the sample, which is 5. Okay, this one. Okay. So it means that here 5. Okay. You saw for SST 5 multiply by the y bar, which is 28.82 minus 19.887, right? This one is square plus, I hope you understand what I'm putting here. It's a bit messy, but I hope that's clear. Okay, and then the next one is 5 multiplied by 23.98 minus 19.887 square. Okay, this is actually a bracket here. Faham tak, guys? So in order to find this one, you can you have to sum up this term. Yeah, like this one. I give you an example for the A and B here. 5 is the sample size. There are 5, right? Multiply by the YA, which is 28.82 minus the mean, overall mean, because this one is overall mean. I'm referring to this formula, 19.887, and the whole thing here is square, plus the expression for the next one, the B, C, and so on. So the summation of this will give you SST. Okay, you can try it later. You can maybe, you understand first how you solve for this formula, and this figure I just put it here. Maybe you can try to see whether it makes sense or not with your understanding. Okay, so that is SST. And how we're going to solve for TSS, because without TSS we do not know what is SSE. We don't have to solve SSE by using the formula, because as I mentioned just now, SSE is equal to TSS minus SST, right? Okay, now we have solved for the SST. We need to solve for the TSS. So the TSS is a bit tedious here. The one is the most tedious part. So this is the original data that you have, and you have to extend the table by adding another 6 columns or maybe 7 columns. This is total. Okay, 6 columns. So how are you going to solve for this? You know the value of the overall mean is 19.887. Y overall is 19.887. So for each of the number, the data, you have to solve for this one. So Yij is referring to each of these points. Okay. So for example here, here is 19.4 minus the overall mean 19.887 square, you got 0.2368. Okay, so now here you can see there are 6 decimal points. You can actually just keep 4 decimal points is enough, but do not make less than that, because otherwise you got not really accurate value at the end. Okay, so this one is actually from the Excel, so that's why we just take it all the figures, but you can maintain 4 decimal points for this one, 4, not less than that. So the same thing goes for the next one, 17.7 minus 19.887 square, you got 4.7815, and you solve for it for the rest of it. So Yij is referring to each of the data. You got it? That's how you got all the values here. Okay? Is it clear, everyone? Hello?
Yes, doctor.
Okay. So it looks tedious, but if you understand it, you put it very properly, then it doesn't really that difficult. Okay. So once you solve for all of this, you have to find what's the summation for every row like this. So 51.9144 is actually the summation of 0.2368 plus 4.7815 plus 8.33 plus 0.66 plus 31.21 plus 6.69. Okay, this is 51.91, and you solve for every row. Okay, so once you solve for every row, then you sum up all of this. That's why it's a bit tedious, I know. 51.91 plus 217.58 plus 297.554 plus 319.9537 plus 242.9657. At the end, you will get this 1129.975. Okay, so please make sure that you keep the 4 decimal points at least, so that in order to get an accurate value at the end. Okay, so that's how you got the TSS 1129. You sum up of all this, but first you have to solve for the values inside for this Yij minus Y bar, double bar square. Okay, so once you get the TSS, you know what's the SST, so you can solve for the SSE. TSS minus SST, you got SSE. Okay, so that is how you solve for TSS, for SST, for SSE. So this is the most tedious part of the ANOVA. Okay, so once you got the values just now, you fill up these values. This one, and also this one. Okay, so when after you have solved that, that would be much easier, because for the mean square is SST divided by DFT. You got this one, meaning to say 847.05 divided by 5, you got what, 69. And this one is 282.93 divided by 24, you got 11.79. That is mean square, MST and MSE. For the F value, this one is equal to 169.41. This is actually MST divided by MSE, right? So 169.41 divided by 11.79, you got 14.38. Okay, so that's why you must have this table, and this one is the calculation table that you also have to provide in your workout. Okay, right, any questions so far? We're not done yet. We're just up to F calculated. This is F calculated. You're not done yet, F calculated. So the next thing, you have to find the F table or critical F. Here we term it as critical F, but you have to know that it's from the table. The degree of freedom is 5 and 24. Is it 5 and 24? Yeah, 5 and 24. Okay, so I've teach you just now how to use the table, and we know that the value of alpha that we refer to is 0.01. So in the table, we are referring to 5 and 24, right? 5 and 24. Let's have a look at the table. 5 and 24. Oh, we don't have it here. Oh, you can refer to your table. I don't have the full table here. So it's given the value as 524. Okay, you should refer to your table, but the value is given as 3.9. Okay, so now we are comparing with the F calculated, which is 14.38. Okay. So 14.38 is greater than the F critical. Yeah? This one and this one, right? So we accept, we reject the null hypothesis. That is the decision. This is the decision rule. So we reject the null hypothesis because this one it falls under this situation. So the decision is to reject the null. Reject null, or you can also say accept alternative hypothesis. It's opposite 10, so it's either one. So you accept the alternative hypothesis. So that is the decision. Conclusion is that you have to say proper sentences. It will be 0.01. Okay. The experiment provides evident real differences. So there is a difference in the mean and level in the seedlings. Okay, there is a difference. that is the conclusion. Okay, you cannot say the conclusion as accept null or accept alternative only. You have to say, you have to mention back what is the problem is all about. I mean, what the hypothesis that you set for the problem. Okay. All right. Any question, guys? So that's basically what today's lecture is all about. I know it's a bit like tricky for you to, but once you practice a lot, then you will know what to do next and next. Yeah? So like this one, so this part is actually for you to solve TSS, SST, and SSE. Yeah? DF, you can solve it easily, right? And after you solve the SST and SSE, you can easily find what is MST and MSE, and finally F. Okay, so the trickiest part is this part lah. But you have to know what you're looking for here. So that's why you go for the easiest one first, and then finally you go for this one. Okay. Right, I think you will do better if you do more exercises. So I give to you on Elite some additional exercises. I think like there are 4 questions. That's enough for you to familiarize yourself with all the steps of ANOVA. Okay. So I hope that you can do it afterwards or at home. Yeah, this week maybe. Yeah. Is it okay, guys? And I would like some volunteers next week to demonstrate to your friends how you solve question 1, question 2, question 3, and question 4. Okay, can you guys go to your Elite if you have data? Yeah, I have uploaded the questions on Elite. Okay, you can see additional exercises. LU3 lecture 1. Okay, I think there are 4 questions, not mistaken. How many questions? 1, 2, 3. Oh, 3. 3 questions. So I need 3 volunteers next week for you to teach your student, to teach your friends how to do it. Any volunteers or any? You can actually work in a group, and then maybe only one person mention it. You can just solve it by writing it on a paper, okay, and then scan it. And on next week, you can just share whatever the workout that you have come up with, okay, and you can share with your friends. If you teach your friends, you will actually learn better and you will remember better. Seriously. So I need 3 volunteers next week. Perhaps you have to do all, and then you can see how your answers differ or compared with your friend's answer. But I need 3 volunteers next week. Okay. Ken, is it possible? Okay, guys.
So okay, Doctor.
Okay. So basically, you just have to do all the questions. Okay. If there is no volunteer, I can just pick up any of you to present. You don't. Okay. So okay, that's your homework lah for this week. Okay. So we'll discuss the answers for the additional questions next week. Okay. Right. So anything more before we disperse? Yeah, anyone who wants to scan your attendance? Does it for today? 21 people or 22? If you can't join the live lecture, okay, I have recorded it. I try to record it every time, so you can just refer to the YouTube channel, or I put it also on Elite. Okay, so you can always refer to all those recorded lectures. Yeah? It's not actually it's not that I force everyone to join the live session every time. Okay, So those, I mean, I would do the live session or live lectures, but if you can't join it because of the internet connection, you can always refer to Elite and you can always refer to YouTube at any time. Okay, so I hope that it would not, it would not really burden you in that sense. Okay, right. So that's all for today. So just to go through again what we have covered, just to give you a very proper way of wrapping up the lectures for today. Okay, so we have covered what is ANOVA, why we use ANOVA. Yeah, you have to know that ANOVA is used when we have more than two samples. When we compare more than two samples, so that's why we use ANOVA, right? And then what we have to do in ANOVA is all the steps that I mentioned just now. Okay, we set the hypothesis. We let's have a look at the steps. Okay, we do the calculation in terms of you have to generate the ANOVA table. Okay, ANOVA table, and then you have to find out what is the degree of freedom, what is the mean of each group treatment or sample. You have to find what's the overall mean, and then what's the SST. Okay, that's on the method that I mentioned just now, the formula. And then what is TSS? From there, you can know what is SSE. SSE is equal to TSS minus SST. And then you have to calculate what is MST, what is MSE, right? I hope that you got what I said just now here by referring to the table. And then you have to find what's the F calculated. And you keep the F calculated, you have to find what's the F table. So in finding the F table, you have to know what's the degree of freedom of treatment and degree of freedom of the error, because you need to refer to that. And also you have to know what's the alpha level that you are referring to. Okay, if it's not given, then you have to define by yourself. Then you get the F table, then you compare the F calculated and F critical or F table, and you have to know what's the decision rule. Yeah, so if the F calculated is greater than the F table, then you you reject the null hypothesis, and the other way around. Okay, and at the end you make a conclusion. So when you make a conclusion, you have to be specific with the problem. What is the problem is all about what sample. You have to mention it specifically. Okay, so that is what ANOVA test is all about. Okay, I've given you an example, and then I hope that's clear. Okay, right, any question before we discuss?
No, doctor.
Okay guys, any question before we discuss? No question?
Clear, doctor.
Okay, thank you. All right, so I hope that you will do the extra exercises. Yeah, apart from you have to first understand the examples given in the lecture, and then you do the exercises, 3 questions. Okay, that's good for you in order to understand better. And we'll discuss next week. Okay, I need you guys to 3 of you maybe, or 3 groups to present. Okay, you just have to do it on your paper, scan it, and then perhaps next week you can share the screen and share with your friends how you got the answers. Okay guys? Okay? No clear?
Clear, doctor.
Okay, all right. Okay, so that's all for today. Thank you very much for your attention, for your patience. I'll see you guys next week, yeah? Right, with your solutions for your answers. Right, so yeah, have a nice day. Take care, bye everyone.
Thank you, doctor.
Okay, welcome.
Thank you, doctor.
Okay, thank
you,
you.
doctor.
Have a nice day, doctor.
All right, thanks.